welcome you all to this course on electron diffraction and imaging. As the name of the course itself suggests, okay, it includes both diffraction and imaging. Throughout this lecture series, I have been always using this term electron diffraction and imaging. So, what does it mean by that? That is, this just gives a hint that possibly using this technique of electron diffraction, we can get information about both the crystal structure as well as the microstructure of the sample. Okay. So, so both this information, diffraction gives information about the crystal structure. This we have studied in detail, and imaging gives microstructural information. But there are some subdivisions into it which we will come to shortly. Okay. So, both these techniques, diffraction and imaging, could be done in the instrument called transmission electron microscope. As we hear the name microscope, we think of optical microscope. Yes, in fact, this is quite similar to an optical microscope, where we have a source of illumination. Okay. Then this illuminated light falls on the sample or specimen. It interacts with that specimen and then gives lot of information, or the rays itself, or that the radiation which is falling on it is scattered, and then we use lenses to magnify, okay, and then get images of microstructure with good resolution. Okay. This is what essentially is being achieved. So, when we talk of the source of illumination, okay, it could be a electromagnetic radiation, like in the case of optical rays it is a monochromatic light which we can use it. In the case of transmission electron microscope, it is essentially the source of illumination is high energy electrons. These electrons are accelerated to very high energies, okay, and the voltage which is being applied is made so precise that the beam is highly monochromatic, okay, and then we choose a source so that the brightness of the source is very high. So, when we wanted to get some diffraction information, the diffraction information essentially, or the diffraction takes place in a sample when the beam is highly coherent and monochromatic. Okay. So, both are satisfied in the electron gun which is used in the transmission electron microscope. These aspects have been described in detail in the class. Okay. The beam which is generated from the gun, okay, that is made into a uniform one using a condenser lens, and this beam falls onto the sample. Then this interacts with that sample. Okay. Generally, in a transmission electron microscope, the samples are extremely thin, of the order of the thickness is generally less than 100 nanometers. Okay. So, since the sample is extremely thin, when the beam passes through the sample, okay, it interacts mostly in an elastic manner. So, essentially the scattering which takes place, okay, the scattering is essentially elastic scattering. Okay. So, this is one of the condition which has to be satisfied for diffraction to occur. Okay. And for this process to occur, there are many ways in which we can consider the sample. What are the ways in which we can look at that sample? One, we can look at the sample as consisting of some point scattering centers which are distributed at some periodic intervals in the 3-dimensional lattice. Okay. These scatters, okay, each of these points have got some particular scattering power, and this is called as the atomic scattering factor. That is one way to look at it. The other way to look at it is that since these are atoms which are present at periodic, so there is a Coulomb potential which is associated with it. So, this potential is periodically varying. Okay. So, the electrostatic interaction between the electrons, the charge of that electron, the high energy interacts with the Coulomb potential, and this changes the path of the electron, that electron trajectory. That way also we can consider that scattering. Okay. So, both the processes are used. Okay. In the case of kinematical theory of diffraction, we use this as a scattering process, as point centers which are scattering. And then in the case of dynamical theory, we assume that the incident electron is interacting with the Coulomb potential. Okay. Apart from this elastic scattering, as the electron beam passes through the sample, some inelastic scattering also is taking place. So, this inelastic scattering, okay, which takes place, okay, is used for spectroscopic techniques. Okay. That is one, it can generate characteristic X-rays from the elements which are present on the samples. Okay. Using these characteristic X-rays, we can find out the type of elements which are present, and then we can find out how this concentration of the different elements vary by looking at the X-ray map, and this map could be used to get information about the distribution of the elements in that sample. Similarly, another inelastic scattering process is that as the electron enters into the sample, even before the characteristic X-ray emission takes place, okay, the electron has to knock the primary electron or the incident electron has to knock out electrons from the different levels in that sample. So, the binding energy of electrons to different levels for each atom is quite specific. So, okay. So, the energy lost by the incident electron, okay, that is characteristic of the element which is present on the sample. So, this also could be used to get information of the information about the chemical composition of the sample surface, and this technique is called as the electron energy loss spectroscopy. These two techniques combined together, okay, with conventional microscope, we call it as analytical electron microscopy. All these aspects have been covered in the course. Okay. Then another factor which is important is that, as I mentioned, that here we can consider scattering as point scattering centers, but what is essentially important is that the property of the lenses which we use for magnification, especially the objective lens which we use to magnify the sample. Why we have to magnify that sample? Why we have to magnify? Because when this interaction takes place, the spatial resolution of these interactions, or the resolution both the spatial as well as the depth resolution or the temporal resolution, we talk about it. Especially what we have to look at is the resolution in the point to point resolution in an electron microscope is from one point to another point. The image, the features which can be seen, okay, that the ultimate limit is given by the Rayleigh criterion. That says that the Rayleigh criterion resolution is essentially 0.61 lambda by beta, the angle which it submits with the lens from that point. So, this criterion of the resolution, okay, is what can be theoretically achieved, but what happens in the case of an electron microscope? Because lenses are not perfect, because the lenses are not perfect, okay, the resolution which we achieve is 100 times worse. Okay. What is essentially happening in that sample? That is, for a point object, we do not get a point image as we have studied earlier. Instead, we get a disk of least confusion. Because of this, instead of getting an image of a point as a point image, we are getting, as we can see, this is for a spherical aberration I am drawing it. So, for all the other aberrations also can look at it. So, at the Gaussian plane, if you look at it, there is a spread. So, for a point, this is what it's that intensity is getting spread over that large area. Okay. This brings down the resolution. Okay. Other than that, the most important property which we have studied about any lens is that all the rays, okay, which are scattered from different points on the object are brought to a focus in the image plane, okay, whereas the rays which are scattered from different points on that sample, that is rays which are scattered from various points on the sample surface in a specific direction. Suppose these are all scattered in this particular direction. All these are, by a lens, focuses it, all of them into a particular plane. This is called as the back focal plane. Okay. So, in the back focal plane, we essentially get information about the rays which has been scattered in different directions. They are brought to focus, and this is nothing but the diffraction pattern, or this we can call it as the Fourier's information of that object is available in the back focal plane. And again another Fourier transform takes place, and which gives in the image plane, you get image about the sample. How to draw the ray diagrams, okay, and find out the back focal plane as well as the image plane. Okay. All these aspects we have covered in detail. So, what is essentially important, which is a characteristic of the lens, is that at the back focal plane we get diffraction information, at the image plane we get that image information. If the incident wavelength, incident radiation has got a wavelength which is quite sufficient to resolve individual atom positions, then we should be able to get image of the object, that is the atomic resolution of that object in that image plane. In fact, in modern microscopes this is possible, and this aspect we have covered in the class. Okay. So, this is the most important information about the lens. So, essentially when we use lenses, okay, we get diffraction as well as the microstructure information, and then that is using elastic scattering. Then we use inelastic scattering interaction of the incident probe with the sample, then we can get information about the chemical composition. So, as we started this course, we mentioned that when we wanted to characterize a material, and when we say that a characterization is complete, material characterization, the information which is required about the sample is crystal structure, then chemical composition, then microstructure. From whatever we have briefly discussed and which has been covered in the course of this lecture, all this information could be obtained in an electron microscope. That is the crystal structure information, okay, from the diffraction pattern, chemical composition interaction, chemical composition information from the inelastic scattering which is taking place, and the microstructure information from the magnification of the scattered radiation, we can get it. Not only that, the chemical composition information, okay, using inelastic scattering, we can get distribution of the elements on the samples. So essentially there are different types of microstructural information, okay, which we can get. Okay. So having discussed so far, okay, about the basic aspects of what all information which we can get it from a microscope, okay, what are the different ways in which these different techniques could be operated. Okay. So essentially what we mentioned is diffraction, okay, and imaging. Okay. What are the various modes in which diffraction could be carried out? This aspect which we considered as parallel beam, then convergent beam, then divergent beam. These are all the various types of beams which we can use. Okay. Parallel beam diffraction is the one which is normally conventionally used, okay, to get information about the, to find out the lattice parameter, okay. And in the parallel beam diffraction mode only, we get images of the sample, okay, using specific diffraction beam, that is going for a 2 beam condition, and then using the transmitted beam or the diffracted beam to get information about the bright field or dark field image of the sample. Okay. Then the convergent beam diffraction is used to find out, okay, information about, okay, or this technique itself is called as the CBED, and this technique gives information about the you can be used to get to measure lattice parameter very accurately, okay, lattice parameter, strain in the crystal, okay, then we can get point group and space group information. These aspects we have covered in detail, how all this information could be obtained using convergent beam diffraction. Then these divergent beam are essentially the, because so far in this we considered the beam as a coherent beam. Whenever any inelastic scattering process takes place, the beam turns out to be incoherent beam. If this incoherent beam is elastically scattered again because the material is a crystalline material, then what it gives rise to is what is called as a Kikuchi diffraction. So this Kikuchi diffraction, the source of Kikuchi diffraction, okay, the source of illumination or the source of diffraction is within that sample, okay. Because of that, when we tilt that sample, okay, by the same angle this diffraction pattern also shifts, and this could be used to orient the sample accurately, and also this could be used to find out the lattice parameters quite accurately. Okay. This aspect also we have covered in detail. Okay. Then imaging not only the bright field and dark field, there is another method of imaging which we called as the weak beam imaging. Weak beam imaging is one in which the diffracted beam is made so weak, okay, so that it satisfies the kinematical condition. Okay. This has some advantage, that especially when you wanted to look at the defect structure like dislocations, whether if they have split into partials, okay, what is the separation between them. In the bright field image it is very difficult to find out the separation, but using this weak beam technique we can get information about that. These aspects we have covered. Okay. Then another is lattice fringes, or this is called as a phase contrast microscopy. Those aspects also we have covered. Okay. But what is essentially important is that all these things, these techniques which we have covered, okay, but in reality, okay, if we wanted to understand or characterize a specific defect, okay, what is essentially important, we should be able to quantify the information which we get it. Okay. That is one aspect which has to be considered. In fact, quantification of these various aspects also has been covered in sufficient detail. What all we have done it, I will just briefly mention. Okay. So, first let us look at crystal structure information, how we can get it. Okay. In this we said that we can use diffraction technique to get this information. So, the thing which one has to understand, what is the relationship between crystal structure, diffraction, and there is another concept is that the crystal structure, when we talk of, we talk in real space, okay, and then we have to consider what is called as the reciprocal space. So, in the crystal structure information, crystal structure essentially determination requires real space, okay, then reciprocal space, and this reciprocal space is related to diffraction. So, all these aspects, that is so when we think of a crystal structure, why do we wanted to understand it, or why do we want to get information about the crystal structure? Because the properties are determined by the symmetries which are associated with the different types of crystal structures. So, we know that there are 7 classes of crystal structures are there. Within those 7 classes, okay, we have 14 types of Bravais lattices are possible, okay, in 3 dimensions, and within these 14 Bravais lattices, okay, around each lattice point, okay, we can put different types of motifs. Okay. There are, these motifs can have some specific symmetry which are associated with them. So, the symmetry which are associated with each of these around the motif, okay, what all the symmetries which we can have in 3 dimensions, there are only 32 distinct point groups are possible. Okay. This, when they are arranged around the space lattice, okay, they give rise to 230 space groups. These are all the space groups into which the crystals, all the crystals which they form fall within one of these space groups. Essentially, what is important is that so this information, when we considered, we started with some crystal structure and came, but what is the information which we are going to do when we look at a sample? What we get is the diffraction pattern. Okay. From the diffraction pattern, we have to go and identify what the crystal structure is. Okay. How to do that? That part of it we understand that depends upon, okay, the conditions which are associated with, okay, are what is called as the extinction conditions. How what are the types of reflections which will be present, or the reflections which will be absent, which are the reflections which are going to be fundamentals, okay, which are the reflections in the case of an ordered alloys which are going to be superlattice. If we get these information, using those information we can try identify what are the crystal structure to which this the specific sample belong. Okay. Those aspects we have covered in detail. So, essentially what is important is the type of symmetry which are associated with it. In fact, each of the crystal structures, if we look at it, if for example, if it is a triclinic structure, if we take it, that does not have any symmetry which is associated with it. Okay. If a particular crystal structure, if you obtain, that is with a monoclinic lattice, if you obtain a crystal monoclinic lattice has got essentially one two-fold symmetry. As we have studied earlier, okay, the reciprocal lattice also exhibits the same symmetry of the crystal, and similarly the diffraction pattern also. So, if you look at the diffraction pattern taken in different directions, okay, if you find that only one two-fold symmetry is present along a specific direction, then the crystal has to be a monoclinic structure. On the contrary, if we find that along three perpendicular directions we are able to get a two-fold symmetry, okay, but the lattice parameters are not turning out to be the same in any of these direction, then the crystal structure will turn out to be essentially orthorhombic. Okay. This way, like if you look at hexagonal lattice, then we will find that we will be seeing a six-fold symmetry in the diffraction pattern, we will be observing it, which we have studied. Similarly, in the cubic crystals also six-fold symmetry will be exhibited by the diffraction pattern in one direction. Okay. But looking at but in the case of HCP, only along one direction, along the C direction the six-fold symmetry is exhibited, whereas in the case of FCC, in the diffraction pattern, if you look at it, along four one directions, okay, in the crystal we will be getting this sort of a pattern. Looking at this information from the diffraction pattern which has been taken in different directions, we can try to find out to which crystal system the particular sample belong to. Once we know what the crystal system, from that we can tell what is the sort of property which the crystal should exhibit. Okay. Now, especially with respect to a mechanical property, or with respect to the magnetic property, or with respect to the ferroelectric behavior, piezoelectric behavior, all these properties could be determined. Okay. For which understanding the crystal structure is important, and the relationship between real space and reciprocal space is another information which is very important, is essentially is that when we wanted to mathematically represent a crystal structure, okay, we have to represent it as a periodic one. There are two ways in which a crystal structure could be represented. One, we can represent this crystal as with respect to any coordinate system which we can choose it. Okay, with respect to that, atoms are at different positions, then it can be defined with a vector r equals u into a plus v into b plus w into c, where a, b, c are the lattice parameters along the different directions, and u, v, w, okay, are the distances, different units which you have to take along each of this direction. So, using this vector, and u, v, w, okay, are all integers, positive or negative. Okay. With this, all the lattice points could be described. This is one way to describe. Okay. But if you wanted to describe the periodicity, the way in which we can look at it is that it can be described as a function psi, okay, 2 exponential 2 pi I k dot r. This should be equal to 1. Okay. This is a condition where r is the any vector in the lattice, and k is a vector which is inverse of the period. Suppose a period in some particular direction is r1, then modulus of k will be 1 by r1. Okay. This, how we looked at it is that in this periodic lattice, okay, suppose we allow an electromagnetic radiation to pass through. Okay. Electromagnetic radiation as a plane wave, if we consider it, this is the way we represent it. Plane wave is I equals e to the power of 2 pi I k dot r, okay, where k equals 1 by lambda. Okay, modulus of k equals 1 by lambda, where lambda is the wavelength. This we know very well. Okay. If this wave enters into it, okay, and when the period of the wave, that k, matches with that of the periodicity in a specific direction, then the crust of the wave all will be touching these lattice points. Okay. Similarly, we can find out so many directions, okay, for which different k values we can obtain. Okay. For in all these cases, the k and the r, if you see, the magnitudes are inversely related. Okay. And the direction, if you look at it, that will be in the same direction as the vector r, the k is going to be. So, that is essentially what is being given here. So, if we use that condition, we will be getting a condition like this. Okay. For this condition to be satisfied, k dot r should be equal to, okay, an integer. For all values of integer, this will turn out to be 1. Okay. R, for this value, for any specific value of r which we choose it, there can be many values of k, and this k is has got a magnitude which is inverse of r. So, this space is called as a reciprocal space. Okay. And this space will exhibit all the symmetry of the real space. And another is that for the 3 vectors which we choose, the unit vectors to represent the primitive translation vectors, the translation vectors of the primitive unit cell, okay, then we can find out values of k, k1, k2 and k3, okay, which are going to be translation vectors of the reciprocal lattice, okay, of the primitive lattice, okay, with which we can consider these aspects and the property of the reciprocal lattice, all these things which we have considered. Okay. Why this reciprocal lattice information is really necessary? Because when we consider diffraction, we use the Bragg condition for diffraction. Okay. The Bragg condition for diffraction essentially is 2d sin theta equals n lambda, or essentially what it means is that when a beam is entering into a sample, okay, in a specific direction, okay, that can be with some particular, in vector notation we will call this a k0, the vector direction, and this beam is scattered in a particular direction which is k. This angle which it submits, this will be essentially between them is 2 theta. Okay. And if Bragg diffraction takes place, then sin 2 theta should be equal to, okay, what is going to be the despacing of these planes, okay, or we can see that the sin theta is essentially proportional to 1 by d, or this will be proportional to, we can write it as d star, which is the reciprocal space. So, the information about the scattering angle when the scattering takes place, that from that information, what the information which we get about the sample is in reciprocal space. Okay. From that, knowing the symmetry of the crystal structure, okay, we can go back, okay, and get information about the crystal structure. So, when we study from real space to reciprocal space to diffraction. Okay. So, in the same information we can get it in a diffraction also. When we consider diffraction, what do we exactly do? We consider a plane wave. Okay. The plane wave essentially is we represent it as I equals a into exponential 2 pi I k dot r, where k is the equal to 1 by lambda, where lambda is the wavelength of the incident radiation. Okay. When this wave is coming in this direction, okay, it is interacting with a particular atom, and we assume that it is scattered uniformly in all the direction. Okay. When we wanted to find out the amplitude of the wave in the different directions, okay, then we write that this scattered amplitude will be equal to a by r at some particular distance, okay, into f of theta, okay, exponential kr. This is how we write it. That means that this is 2 pi I, in all the cases I should be there. Okay. That means that this factor is the one which decides, okay, that is, if a plane wave is coming and hitting this sample, how this plane wave is going to be diffracted or scattered in the various directions. If you look at the amplitude of the scattered rays in the various directions, okay, this is determined by this factor. This factor is called as the atomic scattering factor. Okay. This atomic scattering factor, okay, essentially gives information about, in the case of X-ray diffraction, that depends upon, okay, the density of electrons in the sample or the distribution of electron density in the material. That is what essentially that information we can obtain from the diffraction pattern studies using X-rays. In the case of electron diffraction, okay, this f of theta is going to determine on how the incident electron is going to interact with the electrons in the sample. So, it is essentially the electrostatic potential, how that is distributed, that sort of an information which we can get it, or we can say that the atomic scattering factor depends upon how the incident electron, in the case of an electron microscope, it interacts with each of the atom which is being present. Okay. This is that information. But we know in that sample the atoms are present at regular intervals at periodic positions. From each of these positions, the electron wave, the de Broglie wave, will be scattered, okay, with this particular type of an factor. But what is essentially important, in a specific direction, okay, if this is the incident beam direction k0, in another direction from all the atoms, how that scattering is going to take place. If all the scattered waves, okay, their amplitude add together, okay, then we say that the constructive interference have taken place. Okay, that is what it gives rise to a diffraction pattern. All these aspects which we have studied. Okay. Then from the full volume of that sample, that is how many scattering centers are going to be there in the material, we have to take that into consideration. On that basis, then we will be getting that the amplitude phi g will be equal to kr by r into two terms will come, Sg and Fg. Okay. What is Sg and Fg? Okay. And before we go into that, another important aspect which has to consider is that this sort of a diffraction, when we consider it, okay, this is called as the Lovell type of a diffraction. Okay. From this we can find out what is the condition for Bragg diffraction to occur, what is the relationship between them, all these aspects which we have studied. Okay. But what is essentially important is that the total scattering, when we have to consider each atom, when we wanted to describe, what is the way in which it can be described. Okay. One way in which we can describe is that all the atom position, okay, that R can be described as RL plus RU plus RD. That is if it is a primitive lattice, okay, only RL, that is how, or if it is a non-primitive lattice, how each unit cell, okay, can be represented by one point. Okay, what is the position at which it is occurring? RU is how atoms are distributed within the unit cell. RD is suppose in some region a defect is there and the atom is displaced from the particular lattice position, okay, that deviation which is being given. So, this is the one which has to be substituted and this gives rise to these terms. So, essentially in this what will happen is that Fg will be f of I g into exponential 2 pi I h u I plus k v I plus L w I, all these aspects which you have studied. Okay. This gives what is f I g? This is essentially the atomic scattering factor for each atom position in the unit cell, and this f g gives the total atomic scattering the total scattering factor or the total scattering from each of the unit cell. Okay. When all the like that so many unit cells on which the beam is falling. So, this is the one Sg, the number of unit cells which are there in that sample, that gives this information Sg. So, that gives what is going to be the amplitude of the each of the diffracted diffraction pattern which we see in the sample. That amplitude we will be able to get it. Okay. What is essentially important is that in this Fg, okay, we know that depending upon what positions the atom occur, they give rise to special conditions which are called as the conditions for which the depending upon whether it is an FCC or a BCC crystal, okay, what are the extinction conditions, which for which particular reflections, okay, that we will be able to see the whether a constructive interference will take place or a destructive interference will take place. On that basis we can find out, okay, whether it is a body centered lattice or whether it is a face centered lattice or whether it is an edge centered lattice, all this information which we can obtain. And in addition to it, when it has got a glide, okay, symmetry or a screw symmetry, they also give rise to special conditions, okay, for what all reflections which will be present and which reflections will be systematically absent. Okay. Using this information, we can get information about the crystal structure, okay, its point group and space group symmetry could be determined. In fact, that is what is being done in the case of X-ray diffraction. So, X-ray diffraction is used to get information, okay, about the point group and space group symmetry. The complete crystal structure information of the material or the sample we can obtain. But what is important is that this structure factor which we have written, okay, one basic assumption on which all this entire derivation has been done is that as the beam passes through the sample, only one scattering event takes place. Okay. So, this when we consider only one scattering event, okay, this we call it as kinematical theory of diffraction. So, or kinematical diffraction, that is what it is being done. This is valid for the case in the case of X-rays, because X-ray interacts weakly with matter, whereas in the case of electrons in an electron microscope, they interact strongly. Okay. The electron which has been scattered in a particular direction, okay, before it comes out of the sample it could be scattered again. So, multiple scattering can occur. In that case we have to use what is called as the dynamical theory. Okay. So, what we can understand is that In the case of X-ray, kinematical theory could be used to get information about the crystal structure. So, conventional using parallel beam, when we get the diffraction pattern, using those diffraction patterns, if you wanted to determine the point group and the space group symmetry, it is not possible because the dynamical theory is the only one which has to be applied, and because various types of diffraction like double diffraction takes place, the spots which kinematical theory does not allow, those reflections could be present. Because of all this information, generally the electron diffraction, conventional electron diffraction pattern is not used for determining the crystal structure information like point group and space group symmetry. But looking at the symmetry, we can get some information about what are the crystal class to which, the 7 crystal systems to which it belongs to, all this information which we can obtain in an electron microscope. Okay. Then the other aspect which is important is what is this function Sg. Okay. This function Sg gives, I just okay. This will be essentially sin pi this is the sort of an expression which will come, which you might have all remember. Okay. Okay. This, that depending upon the small deviation, okay, depending upon the size of that sample, because A into n represents what is going to be the size of the sample in a particular direction. Okay. Depending upon that size, this will give a condition for the intensity of the diffraction spot to reach a minimum value. Essentially what it means is that if the sample has got an infinite length, then we will get a very sharp diffraction pattern, while if the sample size, okay, is very small, the diffraction spot will have a lot of broadening. So, or in other words, okay, depending upon the extent of sample size in different directions, we are able to get information, okay, about the shape of that sample. So, the streaking will be present in different directions in the diffraction pattern. In fact, in the microscope, since the sample is which is used is extremely small, as I mentioned, less than 100 nanometers, okay, generally streaking is present, okay, perpendicular to the sample thickness, okay, in the diffraction pattern. So, this is what it is responsible for, okay, many imaging characteristics, okay, of the sample. Because of this, even when we tilt that sample, okay, you find that the diffraction patterns, the parallel diffraction, if you take it, the pattern remains for a long time. That is one of the reasons why we do not use it to find out the lattice parameters very accurately. So, essentially what we can make out is that the structure factor, okay, which is given by psi g, and then this particular factor is the shape factor, okay, which decides how the diffraction parts for the diffraction pattern, the streaking occurs in different direction, that information. So, that is why it is called as the shape factor, which depends upon the shape of the second phase particle. Suppose the second phase particle with a particular shape is there, assume that it is not a spherical one, it is an ellipsoidal one. So, one direction it has got a major axis is very large size, and the minor axis is essentially a small in width. So, because of this, okay, we will be getting streaking in different directions, and in fact looking at the streaking itself, as we have learned, we can find out what is going to be the morphology of the precipitates. That information we can obtain from the diffraction pattern. Essentially, okay, what we have done so far is overall we have covered what all information which we can get it using the various types of diffraction. Okay. Similarly, okay, if we use the imaging capability of the microscope, okay, because as I mentioned, image plane is the one in which the rays which are scattered in different directions, okay, brought to a focus. Okay. By choosing either a transmitted or a diffracted beam, okay, we can get images. If we use only the central beam, undifracted beam, okay, then we call this as bright field image. And if we use any of the diffracted spot, because if from some particular region diffraction is taking place, okay, more diffraction is taking place, that region will appear bright in the image. Okay. So, correspondingly in the bright field image, that region will appear dark. Okay. So, normally bright field and dark field could be complementary to each other. These aspects of it, all the details we have covered in the class. Okay. Not only that, I had also mentioned that there are various modes in which this imaging could be done. Either if you wanted to image a dislocation, okay, then what we have to do is that we have to use in a low index Sonaxis pattern which we have to take it, and if we try to image the dislocation, all the dislocations present in the sample could be imaged. Okay. Suppose we wanted to get or quantify or characterize the particular type of a defect, then we have to image the defect using different G vectors. Okay. That aspect of it we can use it to get in that case, okay, we use a two beam condition, that is one central beam and a diffracted beam which is used. And then the other case is that if we choose so many diffracted beams, okay, allow all of them to interfere again, okay, that will give rise to a lattice fringe contrast which is called as a phase contrast in microscopy, and that could be used to get information about the distribution of atomic distribution or the atomic resolution microscopy. Okay. These are all the various methods and some classifications I had given how to go about to get it. What we will do it is that in the next class, okay, so far we have covered up to diffraction, okay, the image part of it, okay, how we can characterize that image, because we just mentioned that bright field, dark field could be obtained, but what is essentially important is that how these images, different defects, how we characterize them looking at the image. Okay. These aspects we have studied. A brief summary of it, we will take it in the next class. I will stop it here.